The title of this work is Strategic Overview on Fuel Cell-Based Systems for Mobility and Electrolytic Cells for Hydrogen Production. The authors of this work belong to the Fuel Cell and Hydrogen Research Group from the Department of Mechanical Energy and Management Engineering of the University of Calabria. I am Corigliano and I am the speaker of this presentation. It is already possible to define a primordial hydrogen economy, as there are already the technologies necessary for its production and consumption. The production of hydrogen on our continent would also favor the creation of new jobs, as most fossil fuels are extracted and processed outside Europe. About 1 million new jobs could be created by 2030 and about 2 million by 2050. Hydrogen will play a fundamental role in the energy transition. Water electrolysis, supported by green primary source, is at zero emissions of CO2. Therefore, the blue, but mostly the green hydrogen, will be the main target in the fuel industry. Electrolysis represents the scission of water into its constituents, hydrogen and oxygen, by using an external source of energy. Water electrolysis is very welcome to co-participate with the renewable energy technologies and with the smart grids by storing the energy when this exceeds the demands. A fortiori, hydrogen as well as energy carrier can act as an energy storage for environmental and aleatory energy sources. The topic naturally attracts the fuel cells, which are the energy systems par excellence in terms of hydrogen. Fuel cells are attractive for the high performance as efficiency and sustainability, such as to be strongly targeted by the scientific and industrial community. In the era of energy transition, fuel cells can play a central role, both as for stationary and mobile systems. For example, the mobility sector is crucial, as it bears 1/3 of the energy derived from oil. Fuel cells-based applications in the mobility sector are one of the most efficient and cleanest technology for releasing energy from hydrogen. In a fuel cell, hydrogen and oxygen are combined in a catalyzed electrochemical reaction to produce electricity, water, and heat. This representation aims to illustrate a strategic overview of hydrogen production processes via water electrolysis and fuel cell-based mobility by presenting the technological options available and their degree of maturity and the market readiness. In this sheet, the prospectus of the work is presented. Therefore, the work is divided substantially into two parts. The first part consists of the hydrogen production via water electrolysis by investigating the main technologies for producing hydrogen, and the second part is based on fuel cell mobility by detailing the road, the rail, and the marine transport. The term electrolysis comes from Greek and means to break with electricity, and is a process that consists of carrying out chemical transformations thanks to the supply of electricity. The hydrogen generated by the electrolysis of water has a high purity. This purity is about 100%. The electrolysis is the device that puts it into effect, but to work it has to be included in a system as shown in the scheme. In general, an electric source of electricity, photovoltaic, wind, other renewables, nuclear, fossil fuel or biomass power plants can be connected. After the proper process, hydrogen and oxygen are stored to then be used. The electrolyzer depends on the types of the electrolytes used. Therefore, liquid electrolyte is associated to alkaline water electrolysis. The solid polymer electrolyte in the form of a proton-conducting membrane is that used in the PEM electrolyzer, and the solid oxygen ion conducting electrolyte is associated to the solid oxide electrolyzer. In this sheet, the reaction that occur at the electrode side are shown. and therefore is shown also the charge carrier that is different specifically to the technology investigated. But obviously the total reaction is in common, and the total reaction consists of the scission of water into one molecule of hydrogen and a half molecule of oxygen. The alkaline electrolysis is the most major and commonly used electrolyzer technology, especially on a large scale. It addresses the crisis of relatively high energy consumption, installation costs, maintenance costs, durability, and safety. In alkaline solutions, which is normally 20–40% potassium hydroxide used as an electrolyte. Other electrolytes are also used, such as sodium hydroxide and sodium chloride. There are operating temperatures between 60 and 80 Celsius degrees and operating pressures up to 30 bar. The use of a liquid and corrosive alkaline solution is one of the main disadvantages. The PEM electrolyzers use the solid polymer membrane electrolyte, known as natrium. They have the advantage of having a wide operating range, whose characteristic is very suitable for matching with renewables, especially for high fluctuations of electricity. This makes the PEM electrolyzer the most suitable. Technically, this is due to the fast response of the transport of proton neutron. Another advantage is the electrochemical compression. The PEM can produce compressed hydrogen without a compressor. Currently, the main disadvantage of PEM electrolyzers is the high cost of production for using noble metal as catalysts. The SOI technology belongs to the high temperature systems. As a result, the electrical energy requirement is lower than that for conventional electrolysis, and the system's efficiency is higher. SOI devices need to be warmed to temperature in the range 80, 100 and 1000 Celsius degrees to be efficient. This energy source can be accomplished by using solar, geothermal, or recovered waste heat to make soil totally renewable and clean. This technology can count on raw material abundance. In fact, both yttrium and zirconia, that are the main constituents, are abundant materials. Soil performance grew up by more than 2.5 times over the past 15 years. These improvements have impacted the degradation rate, which is passed from 40% over 1000 hours to 0.5%. Long-term tests demonstrated a lifetime enlargement from 6 months to 2.5 years. It is very suitable for steady and massive operations, but it has to be underlined that the SOI electrolyzer is not yet cost effective, but it is about to perform the next step to be ready for industrial scale-up and for wider industrial production. The research is now involved in lowering the temperature. Here we have the summary table, for which we can highlight the specific energy consumption. We can see that the SOI electrolyzer is the most efficient, although it is not the most rare. What about the fuel cell-based mobility? Fuel cell plays a primary role thanks to their high performance and sustainability. Hydrogen and fuel cell technologies are identified amongst the new energy technologies needed to achieve a consistent reduction in greenhouse gases by 2050. The next generation EU plan is strongly focused on hydrogen mobility. Fuel cells are usually used in hybrid powertrains to support an energy storage system composed of battery, supercapacitor, and/or flywheels to face the life cycle's sudden oscillations. The energy storage system presence produces efficiency and performance improvements for two reasons. It allows fuel cells to work in quasi-steady-state operations and regenerative breaks to recover energy during decelerations. It has to be underlined that hydrogen has reached the cost competitiveness, since the grey hydrogen cost is now comparable to that of oil. What about the road transport? Fuel cell powertrain systems are very welcome in the transportation sector, thanks to the high competitive energy density of the hydrogen energy system storage. Compared to the current battery electric vehicles, the latter is about 6-7 times higher. 1 kilogram of stored hydrogen provides an autonomy of 100 kilometers. That is comparable to a full fuel tank of current combustion engines. Fuel cell vehicles offer several key advantages, which fit with the features demanded by drivers: functionality for a large driving range, habitability for passenger cars, and a large load capacity for commercial vehicles, faster charging, low operating costs, safety, and reliability. It is expected that by 2030, 1 in 12 cars sold in Germany, Japan, California, and South Korea will be powered by hydrogen, and more than 350,000 hydrogen trucks will be operated. What about the rail transport? Two classes can be broadly distinguished: low and high power demanding trains. The low power mainly regards tramways and touristic rails, which require a moderate power amount with maximum values lower than 600 kilowatts. PEM fuel cells are used as the prime mover and generally have sizes lower than 250 kilowatts. The hydrogen consumption is approximately 0.2–0.3 kg per kilometer. The high power demanding rails are passenger and freight trains for regional and interregional routes. Also for this case, PEM fuel cells are the most used, but few examples of soft-based powertrains are numerically developed and tested. The fuel cell size for this kind of trains is commonly exceeds the 200 kilowatts. The PEM fuel cell trains consume about 0.3 and 0.5 kg per kilometer of hydrogen. The soft-based trains use approximately 7 liters per kilometer. In PEM-based railways, 350 bar tanks are used, while the soft-based powertrain, the storage is similar as the conventional gas train. For small and mid-sized ships, such as mini vehicles, small boats, and ferries, PEM fuel cells are considered in the size of 150 kilowatts, and hydrogen is used as the only fuel input. For large-size applications, such as vessels, yachts, and real-scale ships, both PEM and soft can constitute the primary movers of the vehicle, with sizes larger than 50 kilowatts. In PEM fuel cell-based powertrains, only electrical demands are provided, and hydrogen or methanol are the fuels. In soft-based systems, cogeneration applications can also be evaluated, supplying the electrical and thermal energy. Here we have a summary table. In conclusion, water electrolysis has shown several potentials in the energy transition. Amongst the most major technologies, alkaline and PEM electrolyzers are considered the most reliable water electrolysis units. Solid oxide electrolyzers are very prominent, but research is still needed to foster the advancements in such technology. Hydrogen and fuel cell mobility will be diffused concurrently to the diffusion of hydrogen production and the refueling station, strictly related to the lowering of the cost of the hydrogen production. In this regard, the efforts for hydrogen mobility are very supported worldwide. PEM powertrain is the most targeted, since it has low temperatures and has a fast startup and working operations. Solid oxide fuel cell powertrain is not mature yet. It finds power demands, and it is usually in hybrid configurations with conventional propulsive systems. Taking into account increasingly restrictive laws about pollution, fuel cells-based systems will be fundamental, and their role will be strong in the field of the energy transition, circular economy, and in the industry and 1.0. Thank you for your patience.